So today's lecture is lecture 10 and it's going to be on chapter 19. We still have 2 reactions and most of the lecture going to be practice. So any other question before we dig deeper toward chapter 19? Actually, there is another question that I'm getting directly after the exam. Will there be extra credit in this class? Yes, there will be an opportunity for extra credit in this class, about 5 to 10 points extra credit. I didn't decide yet. It's fine. Open book, open notebook. You don't need a proctor. For those who are in person, you don't need me to proctor you. And I'll tell you more about it in week 5 of the class. So if you feel like, my grade wasn't what you wanted and you wanted like slightly higher grade to get an A or a B or whatever is the grade, there will be more than one opportunity for extra credit, but at least there is at least one opportunity for extra credit. I think. So in the last lecture, we discussed a couple of different reactions of chapter 19. As usual, I uploaded the reaction concept map, non-inked, for this chapter, without this alpha-beta unsaturated aldehyde and ketone, and the inked one. As usual, it is preferential that you print out the non-inked, then fill it yourself, and take the inked one as a reference. Keep kind of comparing them, and if I were you, as I'm doing the OWL homework or even the EOC, I would put this reaction map close to me, refer to it the first 2 times, then the 3rd time try to put it aside and depend on your memory as you're going. So the reaction that we're going to discuss today is special, and it is not for every ketone or aldehyde. It has to be an alpha-beta unsaturated ketone or aldehyde. What does that mean? It's a fancy name to say that there is a double bond between the alpha carbon, which is the neighboring carbon of the carbonyl, and its neighboring carbon. Or in other words, if you look at it, the C double bond C is one single bond from the C double bond O. This is what an alpha-beta unsaturated ketone or aldehyde is. This reaction that we're discussing in here, it only applies if the alkene or aldehyde is an alpha-beta unsaturated ketone. The nucleophile that this reaction needs to happen is organocopper lithium. We call this organocopper lithium, and it is called so because it is an organic, which is the R, 2 of them, copper and lithium. It's the nucleophile should be either the organocopper lithium, where the R is kind of, you can think about it as it's going to be the nucleophile, the cyanide, sulfide, or RNH2, or a neutral nucleophile RNH2. So if we look at the starting material and the end material in here, if it was just a ketone or aldehyde, what we're expecting is the nucleophile attacking the carbon of the carbonyl, right? This is what we discussed all over the nucleophile, whether they were neutral or a charge for lecture 9, for lecture 8. Now we can see that the nucleophile, if we compare the starting material to the end material, the nucleophile ended up connected to the beta carbon. So it's a reaction in which the nucleophile attacks the beta carbon instead of the carbon of the carbonyl. And here is the question. How would you explain? This is a fact. If I start with alpha-beta unsaturated ketone or aldehyde, and I use one of these nucleophiles, not every nucleophile, these particular nucleophiles that I listed in here, I would end up with a nucleophile on the beta. How would you explain this fact? Okay, stop the video, think about it. For the nucleophile to end up on the beta, what does that tell you? The beta carbon has to be electrophilic, right? A nucleophile has to attack an electrophile. It's not going to end up attacking a nucleophile. At this structure in here, in this Lewis structure, the beta is a nucleophilic. It has a pi bond, right? And pi bond is high density of electrons. So looking at this Lewis structure or the structure of the molecule as is, it looks like a nucleophile is attacking a nucleophile until we take another look at this alpha beta unsaturated ketone. And it looks like this has a resonance structure to it, and the reason behind it is that this double bond is one single bond from the carbon of the carbonyl. In other words, it's conjugated. That means it has a resonance structure. Let's draw that resonance structure and see, would the beta carbon be electrophilic in that case? So always the flow of electrons from the high density to the low density. So the electrons will flow from this to this. That always I'm gonna use a double-headed arrow to represent a resonance structure. And looking at the alpha beta, now the beta is a carbocation in this resonance structure, while the carbon of the carbonyl is partially positive. In other words, when it is, remember that the resonance structure, that means it is neither on that structure nor that, it's somewhere in between. So that beta carbon has an electrophilic properties to it. And this is why when we have nucleophiles that are strong enough that as the reaction goes on, it directly attacks the beta, that's when we end up with a nucleophile on the beta. Now, if the nucleophiles attack the beta, according to this, if a nucleophile now attacks the beta carbon, which is the electrophile, we're gonna end up with this in here. I'm keeping the same colors so that you can see it. Now the next step, as you can see in here, is H3O+, which is mainly a source of H+. So this in here we call enol. That's mean ene, a double bond, and ol, and OH. This enol, we have a chapter, a whole chapter to discuss how the enol change from an enol to a ketone. So you just have for the moment to trust me that this enol gonna change to the keto form. So go from a C double bond COH to a C double bond O. Then later on, when we get to the chapter that is related to that, I'm gonna discuss with you where that's come from. In other words, when I have an alpha beta unsaturated ketone, I have one of the nucleophiles that I listed, organocopper lithium, Cn minus, sulfide minus, or RNH2. Those gonna end up on the betas. The C double bond C is not there anymore. Now it is in the enol form that goes to the keto form. So I just have to kind of bring your attention to one thing, that Grignard is not one of these nucleophiles. As I listed in there, it's either organocopper lithium, sulfide, cyanide, and amine. Grignard, even with an alpha beta unsaturated ketone or aldehyde, it's gonna attack the carbon of the carbonyl. And this is why it isn't listed in here. So keep that in mind when we're doing this. Does this make sense to you guys? All right. Now, let's try an example. So in here is the question is what are the major product Z, and in here Z means the product. I called it Z in the above reaction. So stop the video and try to do this. Your answer is D. D is the right answer. So in here the first thing that you should recognize is that it is an alpha beta unsaturated ketone. We have one of the foreign nucleophiles that attack the beta carbon in a case of alpha beta unsaturated ketone. So we're expecting only one of the R's to end up on the beta, because after the first R is added, which is the first methyl in this case, it's not electrophilic anymore. It's not, that beta carbon is not electrophilic. So one of the methyls gonna end up being connected to the beta. The double bond between the C double bond C is now broken, and we end up with this. In other words, this is the methyl coming from this in here. Now, this organocopper lithium, the R, which is in this case is a methyl, can be anything. It can be a double bond, a C double bond C, a phenyl, a vinyl. So there are no limitations of that in there. of what I can use in this case. So it could be a CH2 double bond CH2. That would still be okay. It could be a phenyl, and I can keep going, so there are no limitations. Go ahead.
So for organocopper lithium, is it always going to add just one of the methyls?
That's right. For organocopper lithium, although we have R2 in here, like 2 methyls, 2 ethyls, it's going to add only one. And it is to the beta. Now this reaction by itself is powerful. I'm adding R groups. I'm adding nitrile, which we said it can open the door to 2 different functional groups, right? The carboxylic acid and the amine, if we reduce it or hydrolyze it. So it is adding carbons to the beta, and this is very powerful because in all the reactions we discussed before in this chapter, the beta never been an active side that I can add functional groups to it. And we're gonna see today in the multi-steps how we're gonna use that. All right. So the first question first, you have to answer what is the product of the reaction that I circled in blue. So stop the video, try to do that. Most popular answer is D, and D is the right answer. So in here we're starting with an alpha beta unsaturated ketone, yet I'm using Grignard, which is not one of the 4 nucleophiles that end up on the beta if it is an alpha beta unsaturated ketone. I put this in the same slide with the organocopper lithium so that it's a reminder for you when you're studying that Grignard reacts in a different way than the others. So in here what's going to happen is the Grignard will attack the carbon of the carbonyl, adding a methyl, and I'm going to put it in blue so that you can see it, and then it's going to be the oxygen will pick the hydrogen from the H3O plus to end up with D. The double bond, the C double bond C should not be affected in this case. On the other hand, if I started with exactly the same compound, but I added organocopper lithium to that, and it is an alpha beta unsaturated ketone, it's a different situation. Actually, the methyl, one of the 2 methyls, gonna end up on the beta carbon. This is the alpha, this is the beta. And this gives us a lot of flexibility, especially when we're doing multi-steps and we wanted a certain compound. I can use either organocopper lithium to end it up on the beta, assuming that we're starting with an alpha beta unsaturated ketone in here, or I can use the Grignard to keep it that the attack take place on the carbon of the carbonyl. Does this make sense to you guys? And I put it on the same slide so that it is very clear the difference between the 2. Make sense? Okay. And I have D to be the most popular answer. D is not the right answer. And I put this particularly in here because I've seen it in exams before, especially in multi-steps, that most of the class would choose D. I kind of know that the class will jump into conclusion, and this is why it is in here, so that you don't do that, neither in the practice exam, nor on OWL, and not even in the exam. So let's start with the first 2 steps in there, that they come together. First of all, this is an alpha beta unsaturated ketone. Hopefully we recognize that. Then we're adding sodium borohydride H3O+. So this is a reducing agent, and it is more specialized for ketones and aldehydes, not for esters, not for carboxylic acid. In here we have a ketone. So this supposedly should reduce the ketone into an OH, into a secondary alcohol. It wouldn't attack the beta carbon. And based on the fact that it reduced the C double bond O, is this an alpha beta on this one? Is it an alpha beta unsaturated ketone anymore? If I add organocopper lithium, would the beta be an electrophilic center? No, because we don't have the C double bond O that is conjugated with it. And this is when we need kind of to understand the reaction and why it ended, the organocopper lithium ends up on the beta, then blindly just remember, oh, every time I see an alpha beta unsaturated ketone, I'm going to end up with the methyl or the R on the beta. It depends. Is it still conjugated? So the two other steps, they mainly not gonna do much. So we're gonna end up with exactly this as a product, which make the right answer is B in this case. Does this make sense? So what I'm trying to say in here, yes, and don't blindly jump in. If we start with an alpha beta unsaturated ketone, please don't directly, especially if there are a couple of steps, don't just decide, oh, let's jump into conclusion, put the methyl on the beta. You have to make sure that first the C double bond O that is conjugated with the C double bond C is still there. All right, let me ask the question in another way. What if we want D to be the right answer? What should I do? Go ahead.
Do the opposite.
Very good. If I flip the reagent, if I put first the organocopper lithium followed by the reduction, I'll end up with D. Actually, let's write that down for you as a when you're doing revision for this. So, in other words, if I start with the organocopper lithium followed by H3O+, I can first end up with the methyl, one of the methyls on the beta, then I undergo the reduction. I can end up with this. Now you're gonna see on our practice exam and the exam, you will be asked, oh, how you go from this one to this one, and you will be given a lot of choices. Some of them would be the reduction before the organocopper lithium, the other the organocopper lithium before the reduction. It's clear if I want D to be the answer, I need to do the organocopper lithium, the beta attack, the attack on the beta before the reduction. Does this make sense to you guys? Yeah, cool. So, from this slide on until like 6-7 slides from now, it's all practice. So I highly recommend that you download the reaction concept map. I already uploaded to Moodle. I have B, the most popular answer, and yes, B is the right answer. So looking at the starting material, the first thing we need to identify, it's an alpha beta unsaturated ketone. It's cyclic, it's actually bicyclic too, connected to each other, but that wouldn't change the story that it is an alpha beta unsaturated ketone. Always look at the difference between the starting material and material. The difference is we have this methyl on the beta carbon, and then this double bond C between the alpha and the beta is not there anymore. So to figure out what is the organocopper lithium, I just have to look what is new that is connected to the beta carbon. And in this case, it is a methyl. So these are the reagents needed. Now the next question is how to go from this compound to this compound in here. Also, you have to choose one of the reagents from here. The most popular answer to be E. E is not the right answer, and I'll tell you why you chose E. And I can see why. It's because it is after exam 1. So this is, we said in chapter 16 that an aryl ketone that is directly connected to a benzene ring, if I add H2 palladium carbon to it, it will be reduced all the way to a CH2. All right, let's go back. Is this an aryl ketone? Is this C double bond O directly connected to a benzene ring? No. So the H2 palladium carbon will reduce it to an OH. So this is why E is not the right answer, but I can see how you thought about it and you related just to the material we learned in chapter 16. Actually, for us to reduce any ketone or aldehyde to totally to a CH2, what we're gonna use, or the reaction that we learned, is Wolff-Kishner reaction, which is the hydrazine NH2 NH2OH minus, or sometimes we write it as N2H4OH minus, and this is the reaction that totally reduces the C double bond O to CH2. Go ahead.
What would the H2 have reduced it to in a single bond OH?
That's right, to a secondary alcohol. So if I add sodium borohydride or lithium aluminum hydride or H2 palladium carbon, it will reduce it to an OH. but it wouldn't reduce it to an alkane. For it to be reduced all the way to a CH2, which is an alkane, we need the Wolff-Kishner reagent or reaction, which is N2H4OH minus, and you're gonna see this often as we go through the multi-steps. Any questions before I go to the next exercise? Okay. In here, the question is, it's a multi-step. I want you to kind of put together how to go from the starting material to this end material. You need to figure out the steps and the reagents. So go ahead, stop the video and try to do that yourself, discussing this. So we're starting this. These are the questions that you should ask yourself, and you're gonna hear me asking you the same questions slide after slide. What are we starting with as a functional group? What are we ending up with? Is there a change in the number of carbon? How many carbons? Which functional group we're going to? First, we're starting with an alpha-beta unsaturated ketone. Just a comparison, a quick comparison. It's clear that I added something to the beta. Then after that, that something changed to carboxylic acid. Now, first of all, adding things to the beta carbon is not an impossibility. We just learned if it is an alpha-beta unsaturated ketone, these are the nucleophiles that I can add. Organocopper lithium, cyanide, sulfide, or RNH2. So one of these, if I add any of these to the alpha-beta unsaturated ketone, it's going to end up on the beta carbon. Now, then the next question for me to narrow it down, which one I'm going to add of these, clearly not the sulfide, not the amine, right? I need carboxylic acid. Then in my mind, okay, what are the ways that we learned in this class to prepare a carboxylic acid? Because this will narrow it down more for me. So we learned that a primary alcohol, if I use one of the strong oxidizing agent like sodium dichromate or chromium trioxide with H+, it will take it all the way to the carboxylic acid. The other thing that we learned with the cyanohydrin is that if I have a C triple bond N, if I add H3O plus heat, it goes all the way to the carboxylic acid plus the ammonium. So in here it becomes easy to see that I can relate the C double bond O, the C double bond OOOH, which is the carboxylic acid, to the nitrile. So I can think about it backwards, saying, oh, you know what? I think, let me try, what if that was a cyanide and I added H3O plus heat to it? This will change to the carboxylic acid. This is what we learned. Now I'm going to go backward and say, oh, is there a way to add the cyanide to the beta carbon if I have alpha-beta unsaturated ketone? Indeed there is, which is adding cyanide. Then the cyanide will end up on the beta. Does this make sense to you guys? This is what I meant when I talked about the cyanohydrin, that always connect the C triple bond N to carboxylic acid, the C triple bond N to a primary amine, because that C triple bond N opens the doors to these two function groups. Does this make sense to you guys? Any other method that you thought about that you'd like me to go over? Go ahead.
Can you do the dimethyl organocopper and then
All right, very good. So she's saying that first we're gonna add the organocopper lithium, followed by the H3O plus. We're gonna end up with this on here. Then I'm gonna use KMNO4 to oxidize this. All right, where did we learn that KMNO4 oxidize a methyl? Was that chapter 16? When the methyl is directly connected to the benzene ring? It has a benzylic hydrogen. Is this methyl connected to a benzene? No. And thank you for suggesting that, because some students also confuse that with it. Then here, this is not a good method because this is not a benzyl. It's not a benzylic methyl. If it was, it will work, but in the first place, if it was a benzylic, it's not getting alpha beta unsaturated ketone. Thank you so much for suggesting that method. Okay. Now, just gonna take this one and discuss what if I take this one and instead of adding H3O plus heat, I added lithium aluminum hydride, H2O. Remember that lithium aluminum hydride reduces ketones, aldehydes, esters, carboxylic acid, C triple bond, and to a CH2 and H2. What would happen in this case? Assuming I have enough, so it's not like one equivalence or a limited amount. What do you think should happen? Go ahead. So we have a ketone that can be reduced by the lithium aluminum hydride, and we have a C triple bond N that also can be reduced by the lithium aluminum hydride. So that would result in the ketone changing to a secondary alcohol and the nitrile changing to CH2 and H2. So what I'm trying to say in here, that keep an eye in the hydrolysis, it's only the cyanide that's going to be affected. The C double bond O of the ketone will not. In case of lithium aluminum hydride, if there is two functional groups in the molecule, we have always to keep an eye on both of them and make sure that we write the right reaction for each. Does this make sense to you guys? Where are we going with this? So in the exam, the practice, or OWL, you could see this as a starting material and this as an end material, or it can be just this as a start material and this as an end material, and you're asked to do the multi-steps. Always link the C triple bond N, or the nitrile, to carboxylic acid and the primary amine. Okay, so in this equation, what I want you to figure out is what are the reagents. It could be two steps, like sodium borohydride followed by H3O plus, to take you from this one to this one, then how to go from this compound, what are the reagents reactions that need to be done to get to this one. So stop the video, try to do it. Okay, so I'm gonna start with the first one. We're going from, always you have to ask yourself the same questions. What is the change? Is there a change in the number of carbons? What functional group we're starting with, which one we're ending up with. So in here we have a primary alcohol. We're ending up with an aldehyde. Is there a change in the number of carbons? So since there is no change in the number of carbons, that tells me I'm going from an OH to a C double bond O. This is an oxidation reaction, right? Because if there is a change in the number of carbons, that's something else. But there is no change in the number of carbons. I'm adding double bonds to the oxygen, that's oxidation. So using chromium trioxide or sodium dichromate will take a primary alcohol all the way to carboxylic acid. So I can't use those. The special reagent that we use, the only reagent that we learned about, that we can take a primary alcohol to an aldehyde, is the Martin reagent. Very good. Using chromium trioxide or sodium dichromate with H plus would not achieve this reaction. It will take it all the way to the carboxylic acid. So this is our first step. Now in here we're going from an aldehyde to an alkene. Is there a change in the number of carbons? Clearly yes. How many carbons more? Because that helps you. 3. There are, if I to kind of map it, and I mean by map it each carbon to each carbon, this is this part in here, and whatever left is what is added to the compound. So the question is, what is the reaction that we learned that I can change an aldehyde ketone to an alkene, and I can add carbons to it? What are, actually let's do in general, what are the reactions that we learned in chapter 19 that we add carbons to a ketone or aldehyde? Grignard reaction, Wittig, we learned also recently that if we start with an alpha beta unsaturated ketone, which is not the case in here, I can add carbons to the beta. So it's either Wittig or Grignard. Now I'm ending up with an alkene. Which would be more definitive? Where is the double bond? The Wittig or the Grignard? The Wittig. Not that the Grignard can be wrong. It depends on the situation. Sometimes the Grignard can get me the alkene if it is the most substituted one. So in here, all I'm thinking about, okay, according to Wittig reaction, wherever is a C double bond O used to be is now a C double bond C with the carbon is a C double bond C with the carbon that has the minus in the alide, which is this one in here. Does this make sense to you guys? So we learned that in the alide, wherever the C double bond O used to be is now a C double bond C to the carbon that has the minus charge. Actually, I created the alide based on the fact, okay, I'm looking, okay, this is a C double bond O, C double bond C. I know that the one that is circled in green is my aldehyde, so everything else is my alide. The carbon that should have the minus is this one that is connected to the C double bond C. Does this make sense? Actually, you can take any alkene and figure out the alide and the ketone aldehyde from which it is made. Does this make sense to you guys? Any question about what I've done in here? You're gonna see this example often. Like this is just a sample of what you're gonna see, that you end up with an alkene, you have to figure out how to prepare it from the alide. Okay. Again, the question in here is multiple choice. So stop the video, try to do it. Okay. So we're starting, I'm gonna ask exactly the same questions I asked on the slide before. We're moving from an aldehyde to an aldehyde. Is there a change in the number of carbons? Yes, one more carbon that is added to this compound. So there are a couple of ways to think about this. One, ask yourself, what are the methods or the reaction that we learned in chapter 19 in which I can add carbons? Two of them, Grignard or Wittig. So now we're between, which one I want to use, Grignard or Wittig? It could be both of them gonna get me there. Then my second question is for an aldehyde. To form an aldehyde, where should I start with? So I'm gonna going backward kind of in my thinking about it. I'm like, oh, the only reaction that we learned that we can do, prepare aldehyde, is starting with a primary alcohol. So I need an OH on this carbon, and I'm gonna use this Martin reagent because this is the only one that we learned in this class, this Martin reagent. Can I use a chromium trioxide sodium dichromate to achieve this oxidation in here? No. Because if I add chromium trioxide sodium dichromate, I'll end up with this being carboxylic acid, and this is not what I want to achieve in here. So I need the OH to be on this terminal carbon. Now, to prepare alcohols in general, we usually do that by the hydration of an alkene. One of the methods is a hydration of an alkene. So if I have an alkene, I hydrated, I can break the C double bond C, add an OH and an H. All right, let's look at this and this one. Is the OH and H added Markovnikov or anti-Markovnikov? Anti-Markov. So to achieve an anti-Markovnikov, BH3 boration, hydroboration, followed by H2O2 OH minus, ending up with the OH on the terminal. Now going backward, looking at this and this, I'm gonna map it. This is this aldehyde in here. Now, wherever is a C double bond O, ended up with a C double bond C. So this in here should be my alide if I use the Wittig reaction. So it's going to be CH2 phosphonium. And I'll end up with that. So this is one of the methods that adds a carbon. Then I'm adding an OH. Then I'm ending up with the aldehyde. So there were clues from the starting material, the end material, and in between. Now, one can ask, oh, can we do Grignard since Grignard also add carbons? Let's check. So if I add one carbon using Grignard, so this is another way to do that. I'm going to end up with the following. So actually, let's put it in a different color for you to see. Can I go from this one to this one? Is this achievable? To eliminate the OH and H, end up with an alkene. And yes, we are in a secondary alcohol. We're going to end up with an alkene. We can either do it by H3O plus heat or POCl3 pyridine, which is elimination of H and an OH. Now the question is this the major or the minor in this reaction? Or is it the only product in this case? Is there any other possibility other than eliminating this OH and one of these H's? Let me ask the question in a different way. Does this carbon of the benzene have any hydrogen to be eliminated? So this is a case where doing either Wittig or Grignard give me exactly the same product, which is exactly the major for both. So either or, whether you go with this method, I'm going to kind of put a split between the two, or the Grignard method, you're going to go exactly to the same results. It's not always the case. Sometimes doing Grignard will end me up with whatever I want as the minor, and the major, which is the most substituted alkene, which is not what I want. Does this make sense? Questions about what I've done in here? Go ahead. These are much easier than the one before. So how to get from this one to this one and from this one to this one. And guys, I need your attention. There is a mistake in the structure. It should be that the double bond right here, not there. Okay. So I'm gonna start with the first one with the same questions as before. We're starting with a cyclohexanone with a ketone, ending up with a tertiary alcohol. The number of carbons didn't change. Actually, if we want to sum it up, this in here is this. So this cyclohexyl in here is what is added. So the question is, what are the reactions in which we learned that we add carbons? Either Wittig, it end up with an alkene, or Grignard, which we change a ketone to tertiary alcohol, aldehyde to a secondary alcohol. So it's become much easier to figure out that this is to narrow it down to a Grignard. And the alcohol that I'm using, I already circled in green what's from the starting material. So whatever left is my Grignard. So I can put iodine, chlorine, or bromine, it doesn't really matter. Magnesium followed by H3O plus at 0 Celsius. So that's much easier than what we've done before. Now, going to the next one, we're starting with exactly the same cyclohexanone. There is a change in the number. We're going from a cyclohexanone to an alkene. we're adding one carbon more and that double bond. So the way that we can add carbons, the two methods that we learned, is either Grignard or Wittig. So there is an increase in the number of carbons, but wherever is the increase, there isn't a double bond. That means it isn't something like this. So it isn't a C double bond C with whatever to be added. So I'm like, okay, let's try the Grignard and see what's gonna happen. So we're adding one methyl. How did I know that I'm adding only one carbon? Because the difference between the two is only one carbon. This is how I'm deciding. So MgI followed by H3O plus at 0 Celsius. We're gonna end up with this in here. And I'm gonna keep the same colors for you to see. So the question is how to achieve going from this tertiary alcohol to this alkene, and would it be the major product if I just do elimination? It might not be the major product and this whole process is wrong. So adding POCl3 pyridine or H3O plus heat, or sometimes H2SO4 heat, it's all the same. It's an elimination reaction in which the OH and an H from a neighboring carbon. So this is a neighboring carbon, this is a neighboring carbon, and this is a neighboring carbon. Now in here there is a plane of symmetry. So whether I remove the hydrogen from this one or this one, I'm gonna end up with this product in here. But the question is this the only one? No. There is another one which is removing this OH in here and the hydrogen from this neighboring carbon. The end result of that is this one in here, this alkene in here. Now the question is the one that the question is asking me about the major or the minor? Looking at this one, this is the double bond, 1, 2, 3 substituent to tri-substituted, compared to this one, 1, 2 di-substituted. So this is the major. Because it's more substituted, this is the minor. So doing this method, which is a Grignard followed by elimination, is the right method in this case. Always you have to keep an eye if the major is the one that the reaction is yielding. Does this make sense to you guys? Questions about it? Okay. I'll come back to that slide. So, the very last reaction that we're gonna learn in this chapter is the reaction of ketones or aldehydes with alcohols. As alcohol in the fact that it has two lone pairs, so it's a nucleophilic. So if I have a ketone or aldehyde and I add to it 2 moles of an alcohol with H+, the reaction is equilibrium. And actually, let me put it in a different color. The end result of that is what we call in here acetal. So what is an acetal? An acetal is a molecule in which the 2 OR prime, think about it as 2 OR prime as an ether, is connected now to the carbon of the carbonyl. So we call this acetal. Actually, glucose and some of the monosaccharides in their cyclic form are either hemiacetal, that means 1 OR prime connected to them, or acetals by themselves. Now, as you can see that the reaction is equilibrium and it needs H+ to happen. The reaction by itself is not that important except in nature and the fact that monosaccharides form hemiacetals and acetals. Now, the reason that we care about this reaction is that we're going to use it in a different way, in a way that we're going to use the acetal as a protecting group. Till now, in all this course, and I know in Orgo 1, you never talked about protecting group. So usually when we're doing reaction outside academia, outside me teaching you, the reactions are much more complicated from what we're showing you in here. Sometimes we need a compound, which is a medicine, that have 3-5 functional groups. And we're doing all these reactions, and we have 2 functional groups that react. And I want to protect one of them, because if I reduce it or I oxidize it, I'll end up with a toxic material that we cannot consume, or we end up with a product that we don't need. So protecting groups are usually very important. Actually, for chemists, as a PhD in chemistry, myself, I was enrolled in a course just for protecting groups. What are the protecting groups that should be used? Not that you need to do that, but I'm just going to show you one of the protecting groups, which is the acetal. So just to kind of get you to the point why we need that. Let's say I have this compound in here that has an ester and a ketone at the same time. And I added enough, let's say enough lithium aluminum hydride and H3O+. Lithium aluminum hydride reduces almost everything. Ketones, aldehydes, esters, carboxylic acid, and I can keep going with that, right? So the result of this reaction, assuming I have enough, is that the ketone gonna change to a secondary alcohol being reduced, and the ester gonna be reduced to a primary alcohol, with this leaving as methanol. So both of them will be reduced, because lithium aluminum hydride is a strong reducing agent that reduces, I can keep going, ketones, aldehydes, ester, carboxylic acid, nitriles. It can reduce all of these. Okay. Now, what if I'm just gonna take it one step further? What if I added sodium borohydride instead of lithium aluminum hydride? Sodium borohydride, we said it is specific. It reduces ketones, aldehydes, but not esters, not carboxylic acids. So the expectation in here is that the ester not affected, sodium borohydride is not efficient enough, while this will be reduced, the ketone will be reduced to a secondary alcohol. Ester not affected. Right, all of these are facts. Now, what if in one of the reaction, what I wanted to produce is this? Not reduce the ketone, so the ketone not changed, is still a ketone, but the ester is now a primary alcohol. Can I use lithium aluminum hydride from the slide? Clearly not. Can I use sodium borohydride? Clearly not. Here where protecting groups is where I start saying, okay, I need a protecting group. I need to protect the ketone until I do what I need to do to the ester, then I would remove the protecting group. So one of the aspects of a protecting group is it reacts with specific groups, not other. And that's what the acetal is. If I add 2 moles of ROH, they will react with the ketone or aldehydes, but not the esters, Now, the second thing about protecting group, I should easily put it in, easily remove it. I don't need to do 5-7 reactions, steps to remove it. And acetal can help in that. In other words, if I want to achieve this in here, I'm going to retake it and go step by step. So if I want to reduce the ester but not the ketone, my first step would be adding 2 moles of ROH, H+. So I'm changing the ketone into an acetal. I want to protect it, and we call this a protecting group, protecting step. The reaction itself is an equilibrium, so I'm going to represent it as so. So the 2 OR prime from the alcohol is going to attach to the ketone. So now I change the ketone into an acetal. Now, one of the things about the protecting group, it should be not that reactive. And the acetal does not react with Grignard. It doesn't react with lithium aluminum hydride. It doesn't react with sodium borohydride. It doesn't react with H2 palladium. I think you get the idea. it doesn't react with anything almost, and this is why it is named as a protecting group. My second step in here is now that the ketone is masked. Think about it as if I put a mask on the ketone. I kind of protect it. I can now do the lithium aluminum hydride step to reduce the ester. So the ester is now a primary alcohol, while the ketone is still an acetal, still masked. Now I need to kind of remove the protecting group. And the easiest way to remove it is by adding H+. And by doing so, I'll go back to the ketone. Wherever is the COR prime OR prime is, used to be a C double bond O, definitely plus the 2 moles of ROH. So I achieved this reaction by protecting. Yes, it is 2 steps more, but I achieved that the ketone is protected, the ester is reduced. Now, when exactly do we need to use a protecting group? Definitely not when I want to reduce both, right? Not when I want to reduce the ketone, not the ester. It's cases, I can't give you a general term for it. It's more critical thinking. Every time you see it, you kind of think, oh, did both of them react or one? Can I protect the ketone from that reaction? And just to make sure that you get the idea, let's do a practice on it. Let's give you an example and see if you can figure out whether the acetal is needed or not. But before I go to that example, any question about anything done here? Okay, so let's go. In here, I just summarized what I said about what is a protecting group and what are the acetals are unreactive with what, so that you have it and you don't have to kind of write everything there. So let's go to this example in here. So which of the following require the use of acetal as a protecting group to give the product? You don't have to use acetal if it isn't needed. You only use it if the reaction is not achievable unless it is there. So you're choosing from one of these. So go ahead, do this. The most popular answer is C. C is the right answer. So in here, you need critical thinking. I can give this example in 3 different ways and the answer is going to be different each time. So just you have to depend on your kind of evaluation of each step. So in here, I'm starting with a ketone, ester. The ester is not reacted, still ester, while the ketone is a secondary alcohol. Sodium borohydride can do that because it reacts with ketones, aldehydes, not esters, carboxylic acids, or nitrile. So simply this is achievable without any kind of protecting group. In the second one, the ketone is changed to a secondary alcohol, the ester into a primary alcohol. That's achievable by lithium aluminum hydride. Now we come to this one. The ketone is still a ketone. The ester is a primary alcohol. Clearly, if I use sodium borohydride, it's reaction number 1. Both of the ketone will be reduced. If I choose number 2, if I use lithium aluminum hydride, the result is the product of number 2. So in this case, I have no way to achieve this without a protecting group. So my first step is adding 2 equivalents of ROH, H+, followed by the lithium aluminum. So this first step is what I showed in the slide before, the protecting step. Lithium aluminum hydride, followed by H3O+, and the fourth step is H+ to get rid of the protecting group. Now let's visit number 4, because this is where most students kind of do the mistake. I'm looking at the ketone. It's now a tertiary alcohol with 1 carbon more. I'm looking at the ester. It is now a tertiary alcohol with 2 same R prime group. So is this a reduction? No way, because we're adding carbon. So what type of reaction is this? This is a Grignard reaction. We know that Grignard reacts with ketones, aldehydes, and esters. So in here, if I had if I add this and I'm gonna add excess of it for it to react with both the ketone and the ester will add 2 equivalents and the ketone will add 1 equivalence. The ester will have 2 same R groups, which is right here. Remember that the ester, if I add 2 equivalents, it add 2 same R groups with tertiary, and the ketone gonna be tertiary. So this is achievable by just excess of that, excess of the Grignard. Now it would be a question mark if the ester changed to tertiary alcohol but not the Grignard, but not the ketone. Then I need an acetal. So as I said, I can give you the same, almost the same starting material, end material, but it will be different depending. You need to critically look at each one of this. Does this make sense to you guys? Yeah. You know what? I'm gonna stop right here, then I'll go over whatever left in the upcoming lectures. So enjoy the rest of your day.